Mercury, the planet. Introduction to Mercury. Basic facts: the smallest planet in the solar system. Closest planet to the Sun. Average distance, 58 million kilometers, 36 million miles. Orbital period, 88 Earth days. Shortest year. Rotation, 59 Earth days. A day-night cycle equals 176 Earth days. Diameter, 4,879 kilometers, approximately 38% of Earth's mass, approximately 5.5% of Earth's. Visibility appears as a bright star-like point, but only near sunrise or sunset. Mercury's position in the solar system. Closest planet to the Sun. Mercury is the innermost planet in our solar system. Average distance from the Sun, approximately 57.9 million kilometers, 36 million miles. That's only 0.39 AU astronomical units, less than half the distance from Earth to the Sun. Orbit shape. Mercury's orbit is elliptical, oval-shaped, not a perfect circle. Eccentricity, 0.21 gives the most eccentric orbit of all planets. This means its distance from the Sun changes significantly. Perihelion. Closest point, 46 million kilometers. Aphelion. Farthest point, approximately 70 million kilometers. When at perihelion, Mercury gets nearly 1.5 times more solar energy than at aphelion. Orbital speed. Mercury moves around the Sun at an average speed of 47.9 kilometers per second, 107,000 miles per hour. Fastest moving planet. Gives why the Romans named it after their swift messenger god, Mercury. Orbital period. Year. Mercury completes one orbit around the Sun in 88 Earth days. This is the shortest year of all planets. Mercury orbits the Sun about 4 times for every Earth year. Rotation and day-night cycle. Rotation period, 59 Earth days, but because of its orbital resonance, a day on Mercury's sunrise to sunrise lasts 176 Earth days. That means a year on Mercury equals 88 days. A day on Mercury equals 176 days. So 1 Mercury day equals 2 Mercury years. Axial tilt. Mercury's tilt equals 0.034, gives essentially no tilt. This means no seasons on Mercury. But extreme differences between day and night temperatures because of lack of atmosphere. Relation to other planets. Order of planets from the Sun. Mercury gives Venus, gives Earth, gives Mars, gives Jupiter, gives Saturn, gives Uranus, gives Neptune. Mercury has no moons, gives unlike Earth, Mars, and other outer planets. Mercury has no rings, gives unlike the giant planets. View of the Sun from Mercury. The Sun appears about 2.5 to 3 times larger in the sky than from Earth. Solar radiation is 7 times stronger than on Earth. Perihelion. Precession. Einstein's contribution. Mercury's orbit doesn't close perfectly. Gives its perihelion. Closest point to the Sun slowly shifts over time. This shift puzzled astronomers for centuries. Einstein's general relativity explained it. Gives one of the first real proofs of his theory. Surface and geography of Mercury. General appearance. Mercury's surface looks very similar to Earth's moon, covered with impact craters, rocky plains, and giant cliffs. No atmosphere to smooth or erode. The surface gives ancient features remain preserved. Impact craters. Billions of years of asteroid and comet impacts shaped the planet. Examples: Caloris Basin, one of the largest impact basins in the solar system. Diameter, approximately 1,550 kilometers, bigger than Texas. Surrounded by mountains 2 kilometers high. Secondary craters formed from debris ejected during the impact. Plains. Large flat regions across Mercury, formed from ancient lava flows after massive impacts. 2 types: intercrater plains, very old, heavily cratered. Smooth plains, younger, fewer craters, cover large parts of Mercury. Scarps, cliffs, huge lobate scarps crisscross Mercury, formed when the planet's core cooled and shrank, causing the crust to crack. Some scarps are up to 1,000 kilometers long and several km high, evidence that Mercury is still geologically contracting. Hollow strange, bright depressions scattered across the surface, likely formed by the loss of volatile elements like sulfur, evaporating into space. Hollows are unique to Mercury, gives not seen on other planets. Polar regions permanently shadowed craters at the poles remain extremely cold, below -170 degrees Celsius. Radar data plus spacecraft confirmed water ice deposits there, likely delivered by comets, asteroids, or formed from hydrogen and oxygen, trapped in surface materials. Surface temperatures. Mercury experiences the biggest temperature swings in the solar system. Daytime sunlit side, up to 430 degrees Celsius, 800 degrees Fahrenheit closing parenthesis. Nighttime dark side, down to -180 degrees Celsius, -290 degrees Fahrenheit, range equals approximately 610 degrees Celsius difference. Extreme, because Mercury has no thick atmosphere to retain heat. Colors and composition, to the naked eye, grayish, rocky surface. Spacecraft images reveal subtle color differences. Darker areas equals older basaltic rock, lighter areas equals younger deposits. Bright spots equals areas with unusual minerals or hollows. Asterisk internal structure of Mercury. Asterisk overall composition. Mercury is a terrestrial planet, gives rocky body like Earth, Venus and Mars. Uniquely, Mercury is dominated by a huge iron-rich core and has only a thin rocky shell. Density 5.43 grams per cubic centimeter, second only to Earth, despite being much smaller. The core radius approximately 2,000 kilometers makes up about 85% of Mercury's total radius. By comparison, Earth's core is only approximately 55% of its radius. Composition: mostly iron, with some nickel and sulfur, likely divided into solid inner core, liquid outer core. Evidence from magnetic field and gravity measurements. The liquid part of the core explains why Mercury still has a magnetic field. Mantle: very thin mantle layer, approximately 400 to 600 kilometers thick. In contrast, Earth's mantle is approximately 2,900 kilometers thick. Suggests Mercury may have lost much of its outer rocky material early in its history, possibly from a giant impact or intense solar winds from the young sun. Crust: estimated thickness 100 to 200 kilometers. Rocky, silicate rich, similar to the moon's crust, covered in craters, lava plains, and tectonic scarps. Contains unusual minerals, including sulfur, that resist evaporation. Planetary shrinkages. Mercury's core cooled, it contracted. This caused the crust to wrinkle and form huge scarps, cliffs across the surface. Estimates suggest Mercury has shrunk by about 7 kilometers in radius over billions of years. Magnetic field connection: the partially molten outer core generates Mercury's magnetic field, though only 1% as strong as Earth's. Magnetic data confirms that Mercury is not geologically dead, gives its interior is still active in some ways. Atmosphere: exosphere of Mercury, true atmosphere unlike Earth or Venus. Mercury does not have a thick atmosphere. Its gravity is weak, only 38% of Earth's, so it cannot hold onto gases. The sun's strong radiation and solar wind constantly strip particles away. The exosphere of Mercury has an exosphere, which is an extremely thin atmosphere-like layer, made up of individual atoms, knocked off the surface by solar wind bombardment, micrometeoroid impacts. It's so thin that molecules rarely collide, gives more like a dust cloud than an atmosphere. Composition: the exosphere contains oxygen O, sodium Na, hydrogen H, helium He, potassium K, trace amounts of calcium, magnesium, and other elements. Sodium and potassium cause Mercury to glow faintly in yellow-orange colors when viewed with special telescopes. No weather or wind. Mercury has no clouds, no rain, no storm. Surface features remain unchanged for billions of years. Source of gases: most gases in the exosphere come from solar radiation breaking down minerals on the surface, outgassing of volatile elements. Micrometeorites vaporizing surface material. Interaction with solar wind. Exosphere interacts directly with the solar wind, creates a thin sodium tail, streaming away from Mercury. Like a faint comet, Mercury's weak magnetic field helps channel some particles toward the surface, creating space weathering. Why no atmosphere? Mercury is too small and too close to the sun to retain a thick atmosphere. Even if gases were released from volcanoes or impacts, they would escape into space quickly. Mercury's magnetic field and space environment. Existence of a magnetic field. Mercury has a global magnetic field, first discovered by Mariner 10 in 1974. This was surprising given scientists expected Mercury's small size to mean a fully solidified core. Field strength, about 1% of Earth's, gives weak, but still significant, origin of the magnetic field, generated by the dynamo effect in Mercury's liquid outer core. Measurements from MESSENGER confirmed the core is at least partly molten, shows Mercury is not a dead planet internally. Shape of the magnetosphere. Mercury's magnetic field interacts with the solar wind to form a magnetosphere, but because Mercury is so close to the sun, the magnetosphere is much smaller and weaker than Earth's. Highly compressed on the sun-facing side. Magnetic tornadoes. Solar wind particles twist magnetic field lines into magnetic tornadoes. These funnel charged particles directly onto Mercury's surface, creates localized surface weathering and changes in chemical composition. Radiation environment. Mercury is bombarded with intense solar radiation and charged particles. No atmosphere to shield the surface. Spacecraft must be specially protected to survive in orbit around Mercury. Unique magnetic features. The magnetic field is not centered at Mercury's core, gives shifted northward by about 20%. This creates asymmetry in how the solar wind interacts with the planet, leads to stronger space weather effects in some regions. Scientific importance. Mercury's weak, off-center magnetic field helps scientists understand how planetary magnetic fields evolve. Compare with Earth's stronger field. Study how solar wind interacts with small magnetospheres, important for understanding exoplanets close to their stars. Orbital and rotational dynamics of Mercury. Orbit around the Sun. Orbital period. Year 88 Earth days gives shortest year of all planets. Average distance, 57.9 million kilometers, 0.39 astronomical units. Eccentric orbit. Mercury has the most elliptical orbit. Eccentricity equals 0.21. Perihelion closest point, 46 million km. Aphelion farthest point, 70 million km, receives up to 1.5 more sunlight at perihelion than aphelion. Orbital speed, fastest moving planet, 47.9 kilometers per second, 107,000 miles per hour. This high speed gave Mercury its mythological name, the swift messenger god. Rotation on its axis. Mercury rotates once every 59 Earth days. Very slow rotation compared to Earth. 24 hours. Axis tilt only 0.034 gives virtually no seasons. Solar day. Sunrise to sunrise, because of a unique resonance. One solar day equals 176 Earth days. That means Mercury's day sunrise to sunrise lasts twice as long as its year 88 days. A day on Mercury equals to Mercury years. This causes extreme heating on the daytime side and freezing cold on the nighttime side. 322 spinnerbait resonance. Mercury is in a 322 resonance with the Sun. Rotates 3 times on its axis for every 2 orbits around the Sun. This unusual balance is caused by its eccentric orbit and the Sun's gravitational influence. As a result, certain regions of Mercury always face the Sun at perihelion. Strange sunrises. If you stood on Mercury, the Sun would appear to rise, stop, move backward briefly, then continue rising. This happens because Mercury's orbital speed near perihelion temporarily exceeds its rotational speed. The Sun in Mercury's sky looks 2.5 times larger than it does from Earth. Perihelion precession. Mercury's orbit shifts slightly with each revolution gives, known as perihelion precession. Classical physics couldn't explain the extra shift, approximately 43 arcseconds per century. Einstein's general relativity solved the puzzle, gives one of the first major proofs of the theory. Mercury, in history and culture. Ancient observations. Mercury is visible to the naked eye, but hard to spot because it never strays far from the sun. Ancient civilizations noticed it, often mistaking it for two separate stars. One visible in the morning before sunrise, one visible in the evening after sunset. Only later did they realize it was the same object. Babylonian astronomy. Babylonians, around 1000 BCE, recorded Mercury's movements. Called it Nabu, after the god of writing and wisdom. Greek and Roman mythology. Greeks had two names: Apollo for morning appearances, Hermes for evening appearances, later unified as Hermes gives messenger god, linked with speed and travel. Romans adopted Hermes as Mercury, their own swift messenger god. The name reflects the planet's fast orbit around the sun. Indian astronomy. In Vedic and Hindu traditions, Mercury is called Buddha, associated with communication, intelligence, and commerce. Day of the week. Wednesday comes from Buddha in Sanskrit, Buddhavara, and Mercury in Latin dies, Mercuriae. Chinese astronomy. In Chinese 5 elements, philosophy. Mercury is linked with the element water. Represents wisdom, adaptability, and communication. Mayan civilization. Mayans tracked Mercury's cycles for use in their complex calendars, associated with underworld deities due to its fleeting, elusive visibility. Alchemy and symbolism. In medieval Europe, Mercury was one of the 7 classical planets. Known to ancient astronomers, symbol is used both in astronomy and alchemy. Associated with quicksilver, liquid metal, Mercury gives fluid, changeable nature. Cultural legacy. Mercury influenced astrology. Gives Mercury rules, communication, intellect, and travel. Literature, art, and astrology traditions worldwide. Exploration of Mercury. Challenges of exploring Mercury is very hard to reach, being so close to the sun. Spacecraft must fight against the sun's strong gravity to slow down into orbit. Requires more fuel and complex trajectories than missions to outer planets. Harsh conditions. Intense heat over 400 degrees Celsius in sunlight. Freezing cold in shadows. Strong radiation and solar wind. Ground-based observations before spacecraft. Mercury was observed with telescopes. Very difficult to study due to its proximity to the sun. Only basic features could be mapped until the 20th century. Mariner 10. NASA, 1974, 1975, first spacecraft to visit Mercury. Used gravity assist from Venus to reach Mercury. The first time this technique was used, flew by Mercury 3 times. Key discoveries. Mercury has a magnetic field. Unexpected. Surface is heavily cratered, like the moon. First images of the planet, covering about 45% of its surface. Messenger. NASA, 2004 to 2015, first spacecraft to orbit Mercury. Entered orbit in 2011, and studied the planet for 4 years. Key discoveries. Mapped 100% of Mercury's surface. Found evidence of water ice at the poles. Discovered unusual surface features, called hollows. Confirmed Mercury is shrinking as it cools. Revealed surprising amounts of volatile elements like sulfur, meaning Mercury is more chemically complex than expected. Studied Mercury's thin exosphere and magnetic field in detail. Crashed into Mercury's surface in 2015 when its fuel ran out, leaving a new crater. BepiColombo ESA plus JAXA launched 2018 a joint European-Japanese mission. To spacecraft MPO Mercury Planetary Orbiter will map the surface and interior. MMO Magnetospheric Orbiter, renamed MEO, will study the magnetic field and interaction with solar wind. Used multiple flybys of Earth, Venus, and Mercury to slow down enough to enter Mercury's orbit. scheduled to arrive in 2025 and operate for at least 1 year. Expected to answer key questions about Mercury's core structure, surface composition, magnetic field, dynamics, exosphere, and polar ice. Future missions, no human missions planned. Environment is too extreme. Robotic landers have been proposed, but face engineering challenges. Future exploration will likely focus on robotic orbiters and landers. To study Mercury as a model for rocky exoplanets, Mercury's role in science, testing Einstein's general relativity. Mercury's orbit shifts slightly over time, known as perihelion precession. Classical Newtonian mechanics couldn't explain the extra shift. Einstein's general relativity provided the missing explanation in 1915. Orbit remains one of the most famous proofs of relativity. Planetary formation. Cluse Mercury has an unusually large iron core relative to its size. Raises big questions. Was Mercury's outer crust stripped away by a giant impact? Did intense solar radiation in the early solar system blast away lighter material? Or did Mercury simply form differently? Studying Mercury helps scientists refine models of how rocky planets form. Interior and geology. Mercury is still geologically active in some ways, shrinking core. Tectonic scarps. This challenges the idea that small planets die quickly. Helps us understand Earth's long-term future and other rocky worlds. Magnetic field studies. Mercury's weak but active magnetic field is unique among small rocky planets. Studying it helps scientists compare with Earth's strong field, understand how magnetic dynamos start, evolve, and fade, predict how exoplanets might behave near their stars. Exoplanet connections. Many exoplanets discovered close to their stars are supermercuries, rocky, dense, and baked by starlight. Mercury acts as a natural laboratory for studying how these exoplanets may evolve. Space Weather Laboratory. Being so close to the Sun, Mercury is constantly blasted by solar wind. Provides insights into how stellar winds interact with planets. Helps predict effects on Earth's space environment and satellites. Astrobiology. Relevance itself is not habitable, too hot, no atmosphere. But studying its ice deposits at the poles reveals how water and volatiles survive in extreme conditions. Important for understanding how water travels around the solar system. Future of Mercury. Exploration and colonization. Robotic exploration. Mercury's extreme environment makes it a prime candidate for robotic missions rather than human exploration. Future missions may include orbiters gives to study magnetic fields, exosphere, and geology. Landers gives to directly analyze surface materials, confirm polar ice, and study tectonic activity. Sample return missions gives bringing Mercury rocks to Earth for study. BepiColombo's legacy current ESH AXA mission, arriving 2025, will map Mercury in greater detail than ever. Study interior structure, exosphere, and polar regions. Provide data to plan possible lander missions in the 2030s-2040s. Human missions. Challenges. Colonizing Mercury would be far more difficult than Mars or the Moon, because extreme temperatures, plus 430 degrees Celsius in sunlight, minus 180 degrees Celsius at night. Radiation. No thick atmosphere for protection. Long days. 1 day equals 176 Earth days. Any human settlement would need to be in polar regions, where ice exists and temperatures are more stable. Possible habitats. Underground bases. Protection from radiation and temperature swings. Polar craters. Some craters are permanently shadowed and contain ice, gives potential for water supply. Solar power advantage. Mercury receives 6.5 times more sunlight than Earth. Great for solar energy, but requires shielding from overheating. Scientific value of Colonization. Mercury outpost could serve as a solar observatory, gives closest vantage point to the Sun. A mining hub gives Mercury's crust, and core may contain useful metals. A testing ground gives 4 extreme environmental technologies that could later be used on exoplanets or other harsh worlds. Long-term possibilities. Colonization is unlikely in the near future, but as technology advances, nuclear power, radiation shielding, autonomous robotics, Mercury could one day host small research outposts. It would never be as comfortable as Mars, but its resources and location make it scientifically important. Comparisons of Mercury with other celestial bodies. Mercury versus the Moon. Both are heavily cratered, airless worlds. Mercury is much denser and has a massive iron core. The Moon has seas of basalt maria from past volcanism, while Mercury's volcanism ended billions of years earlier. Unlike the Moon, Mercury has a global magnetic field. Mercury versus Venus. Venus is called Earth's twin, while Mercury is more like Earth's metallic core exposed. Venus has a thick, toxic atmosphere, gives Mercury has none. Venus rotates backward and very slowly. Mercury has its 3-2 spin-orbit resonance. Surface temperatures on Venus are more stable, but hotter. Mercury has extremes of hot and cold. Mercury versus Earth. Earth is 2.6 times larger in diameter, but Mercury is surprisingly dense. Both have iron cores and magnetic fields. Earth supports life thanks to its atmosphere and water. Mercury is barren and hostile. Mercury's thin exosphere makes it more like a laboratory of raw planetary evolution. Mercury versus Mars. Mars has a thin co-atmosphere. Mercury has almost none. Mars has signs of ancient rivers and potential past life. Gives Mercury has none. Both have polar ice deposits, but Mercury's exist in permanently shadowed craters. Mars once had volcanism for billions of years. Mercury's volcanism ended much earlier. Mercury versus exoplanets. Many exoplanets discovered close to their stars are supermercuries. Gives rocky, dense, scorched worlds. By studying Mercury, astronomers learn how these extreme exoplanets evolve. Mercury is like a window into the universe of rocky star-hugging planets. Mercury, the smallest planet yet one of the greatest mysteries, is more than just a rocky world racing around the sun. It is a time capsule of the early solar system, holding secrets about planetary formation, cosmic evolution, and even the forces of physics that shape the universe. From ancient civilizations that watched it dance across the dawn sky, to modern spacecraft unlocking its deepest mysteries, Mercury continues to inspire wonder. And though its surface is silent and lifeless, its story echoes loudly, reminding us that even the smallest worlds can hold the biggest lessons about our place in the cosmos.